We always hear that computers see the world, right? But what does that actually mean? Well, today we're going to dive into something called raster data. It's basically the fundamental way our digital world sees everything, from a huge mountain down to a single city block. It translates all that stuff into a language computers get, the language of pixels.
Okay, so let's just jump right in with a big question. How does a computer see a mountain? I mean, think about it. It doesn't see rocks or snow or the sheer cliffs the way our eyes do.
It sees millions of tiny squares. That's it. It's like a giant digital mosaic. Every single square is a little snapshot, a tiny piece of the bigger picture. It's how computers take our messy, complex reality and simplify it into something they can actually work with. It's a really powerful idea, so let's break down exactly how it all works.
All right, to really get this, we've got to start small, super small. We need to look at the most basic building block of this whole system. So what is actually inside one of those little squares?
That tiny square, we call it a pixel, or a grid cell. And you can really think of it like the atom of a digital map. It's the smallest possible piece of the puzzle. Each and every pixel is tied to a specific spot on Earth and holds just one single crucial piece of information about that place.
And here's the thing. Every single pixel has three key properties you need to know. Number one is its location, where it is on the map. Number two is its size, how big of an area it covers, maybe 10 meters by 10 meters. And number three is its value. This is the good stuff, the actual data it's holding. That could be anything, elevation, temperature, you name it. Okay, that last part, the value, is super important. It brings us to the next big question. If every pixel has a value, usually a number, what do those numbers actually mean? This is where it gets really cool, where the data starts to tell a story.
So pixel values basically come in two main flavors. First, you've got continuous values. Think of things that change gradually, like temperature or the height of a mountain. A pixel's value might be 32, meaning it's 32 degrees Celsius right there. Then you have categorical values. These are for distinct categories or classes, things like forest, city, or water. It's one or the other.
And check this out. Here's a perfect example. We're looking at a simple grid of numbers, but that number 1 isn't just a 1. It actually stands for forest. The 2s represent urban areas, and 3 is water. All of a sudden, this boring-looking grid of numbers transforms into a map. It's a super simplified but totally readable picture of a landscape.
So we've got a handle on what a pixel is and what its value means. But what about its size? Turns out the size of that pixel is a huge deal. This whole idea is called resolution, and it completely changes what we can and can't see in our data.
And here's the catch. There's always a trade-off. If you want high resolution, you're using tiny little pixels, maybe just 1 meter by 1 meter. That gives you amazing detail, but the file sizes, they get absolutely huge. On the flip side, you could go with low resolution, using bigger pixels, like 100 meters by 100 meters. The files are way smaller and easier to handle, but you lose a ton of that fine detail.
Let's make this super clear with an example. Imagine there's a road, and it's 5 meters wide, okay? Now if our grid is made of 1 meter pixels, that road is going to show up perfectly. It'll be 5 pixels wide, totally clear, easy to see.
But what happens if we switch to a grid where each pixel is 100 meters wide? That little 5-meter road, it's now way, way smaller than a single pixel, so it just gets lost. It gets averaged out with everything else in that big square, and poof, it's gone. It completely vanishes from the map. So that's the key takeaway, right? Your resolution literally determines what exists in your digital world.
All right, so we've got these grids, these digital mosaics, made of pixels that have a value and a size. That's great, but so what? How do we actually use this stuff to make real-world decisions? Well, this is where it gets really practical. Let's put these pixels to work. Let's say you're a farmer, and you're trying to find the absolute best spot to plant a new crop. We can use this raster data idea to solve the problem. First, we create a layer for the slope of the land. In this layer, we're just going to highlight all the pixels that represent flat ground, because that's what's best for farming, right? Okay, flat land is good, but we also need the right amount of rain. So we grab another layer, this time a rainfall map. On this grid, we look for all the spots, all the pixels that get a medium amount of rain. Not a desert, but not a flood zone either. And for our last piece of the puzzle, we need good soil. So we create one more layer. This one is a soil map where the pixel values tell us the soil type. We'll just highlight the pixels that represent the most fertile soil for our specific crop.
Okay, now for the really cool part. We take those 3 layers, our slope map, our rainfall map, and our soil map, and we digitally stack them right on top of each other. The computer then does the heavy lifting. It looks for the pixels that are good on all 3 layers at the same time. And bang! Just like that, the spots that check all the boxes light up, showing us the perfect place to plant.
So, there you have it. From seeing a mountain as a grid of squares to finding the perfect spot for a farm, raster data is this kind of hidden language that helps us understand and shape our world. The next time you pull up a weather map or look at a satellite photo, maybe look a little closer. Ask yourself, what stories are those tiny pixels really telling you?